The objectives of today's lecture will enable you to understand the concept of chirality, optical activity, optical isomerism, and we are going to start the topic of benzene and substituted benzenes. Students, before starting the concept of chirality, let us learn what is a plane of symmetry. A plane which divides an object into two symmetrical halves is said to be a plane of symmetry. For example, let us try to find out the plane of symmetry in a person and a hat. Now, if we are going to pass a plane from the middle of this picture of a person, you can see that we can divide it into two identical or symmetrical halves. Such an object that can be divided into two identical halves by passing a plane is called an achiral object. Similarly, you can observe this phenomena in this hat. If we are going to pass a plane from here, we can divide this hat into two equal halves. That is why it is also an achiral object. A symmetric object is said to be achiral. Here are some other examples. For example, this is a ladder, a fork, a table, and a spoon. An achiral object will always have at least one plane of symmetry. Let us start the concept of chirality. An object that lacks a plane of symmetry is called a chiral object. Students, the opposite of achiral objects are chiral objects. So let us start the concept of chirality. A dissymmetric object means an object which is not symmetrical is called a dissymmetric object. It cannot be superimposed. What is the meaning of superimposed? That if you are going to place one on top of another on its mirror image. A left hand, for example, does not possess a plane of symmetry. Now look at your left hand and try to find out a plane which can divide it into two identical halves. You might not found it. And its mirror image is not a left hand but a right hand. Now place your left hand in front of a mirror. You will see a right hand. The two are not identical because they cannot be superimposed. Why? Because if we were to lie one hand on top of the other, the fingers and the thumb would clash. What are the chiral objects? For example, look at the hand, a foot, a shoes, and an ear. A chiral molecule has at least one asymmetric center, means a center which is not going to provide you identical halves, and does not have a plane of symmetry, means a plane which could divide it into two equal halves. Such objects are called chiral objects. Students, do not confuse the two terms chiral and achiral objects. A achiral object is always a symmetrical object. For example, look at these two structures. They are chiral objects. Why? Because if we are going to pass a plane, it can divide it into two equal halves, like so. Look at the other example. If we are going to pass these planes, it will provide us two equal or identical halves, just like that. Such objects are called achiral objects because they possess plane of symmetry. And students, always remember, greater the plane of symmetries, more symmetrical or achiral the object is. Chiral objects will not have plane of symmetries. You cannot divide them by passing a plane into two identical or equal halves. Students, after learning the concept of chirality, let us try to apply them on molecules and learn what are carbon-based chiral center. A carbon atom which is bonded to four different groups is called an asymmetric, or a carbon atom without a symmetry. For example, look at these two molecules. These two are asymmetric molecules. Why? Look at this carbon atom which is attached or bonded to four different groups. This is a propyl group, an ethyl group, methyl group, and a bromide group. By passing any plane through any axis, you are not going to obtain two identical or equal halves. That is why this molecule is a chiral molecule. And this is the chiral center or asymmetric carbon atom. Similarly, here is another example. Look at this carbon atom which is attached to a hydroxyl group, a hydrogen, carboxylic group and alcoholic functional group. It is also a chiral molecule because it lacks plane of symmetry. Now students, the term asymmetric carbon atom is rather misleading. It only means that a carbon atom that is bonded to 4 different groups and that molecule lacks a plane of symmetry. Such a molecule is called asymmetric, or simply it means without a symmetry. Presently, the terms dissymmetric or chiral molecule is often used for asymmetric molecules. Students, in the previous lecture we discussed about isomerism, we learned the classification and we learned all the details with examples about all these isomers. Today we are going to discuss the configurational isomers, in which we are going to look into the details of optical isomers. Now students, before starting the topic of optical isomerism, let us try to understand what is optical activity. A substance that can rotate the plane of the polarized light is called optically active compound, and this property of the object is called optical activity. You know that electromagnetic light vibrates in all possible planes, but when it is passed through a nickel prism or a polarized lens, only those radiations can pass that are parallel to its axis, and such a light is called plane polarized light. Students, optically active compounds can exist in 2 isomeric forms. The first one is dextrorotatory compounds. The compounds that rotate the plane of the polarized light towards right or clockwise direction, they are called dextrorotatory compounds, and it is indicated by a positive sign. The second one is levorotatory compounds. The compounds that can rotate the plane of the polarized light towards left or counterclockwise or anti-clockwise, they are called levorotatory compounds, and they are indicated by a negative sign. Now students, let us try to understand how do we measure this optical activity of a compound by measuring the optical rotation. The instrument that is used to measure the direction and magnitude of optical rotation is called a polarimeter, and the construction involves a fixed polarizer, a movable analyzer, sample tube containing the sample which is going to be placed between the polarizer and the analyzer, and a source of light. Now students, let us try to understand the working of this polarimeter. Now you can see a source of light, an ordinary light which vibrates in all possible directions. But when such a light is passed through a polarized lens or a nickel prism, it is going to vibrate in only one axis, which is parallel to this prism. Now such a light which is vibrating in only one axis or only one plane is called polarized light. When it is going to pass through the sample solution. What is the sample solution? An optically active compound which can rotate the plane of this polarized light either clockwise or counterclockwise. The rotation of the polarized light is studied through the analyzer, in which we are going to measure the degrees through which this rotation has taken place because of the optically active compound. Now students, let us understand how to carry out this experiment. Light from a source is passed through the polarizer and is polarized. If the sample tube is empty, then parallel position of the polarizer and analyzer gives maximum illumination, and the reading is going to be 0. Now, if a solution of known concentration is going to be placed containing an optically active compound, the solution will rotate the plane of the polarized light at a certain degrees. Thus, less light will pass through the analyzer and we will have less illumination. In order to get maximum illumination, then the analyzer is rotated to a certain angle through which we are going to get maximum illumination again. The angle through which the analyzer is rotated gives the magnitude of the observed rotation, which is represented by alpha, which is the degree of rotation. If the rotation is towards right or clockwise, the compound is said to be dextrorotatory, and if it is towards left or anti-clockwise or counterclockwise, it is said to be levorotatory. Students, let us start the topic of optical isomerism. The definition is an optically active compound that exists in two isomeric forms which rotate the plane of polarized light in opposite directions. These are called optical isomers, and the phenomena is called optical isomerism. As we have already discussed, the isomer which is going to rotate the plane of the polarized light towards right or clockwise direction will be called as dextrorotatory, and if it is going to rotate the plane of polarized light towards left or anti-clockwise, it is called levorotatory isomer. Now students, let us take example of lactic acid and study the optical isomerism in lactic acid. Lactic acid is 2-hydroxypropanoic acid. This is the structure of lactic acid. Now students, observe that this carbon is an asymmetric carbon or a chiral carbon. Why? Because it is attached to 4 different groups of atoms: a methyl group, hydrogen, carboxyl group, and an alcoholic group. Now, it contains one asymmetric carbon. 2 3-dimensional structures are possible for lactic acid. These structures are not identical because they cannot be superimposed on the mirror image of one another. Such non-superimposable mirror images are called as enantiomers. Now students, look at this picture and first of all try to understand the representation of the molecules in a chiral compound. Now, this is the structure of lactic acid, a 3-dimensional structure. Students, always these solid bonds are going to represent those atoms which are on the plane that you are right now observing, the plane of this slide. Means this OH and H are on the plane that you are right now observing. The dotted lines or sometimes the dotted wedge shows that this group of atoms is behind the plane, and the solid wedge always represent that this compound is going to have CH3 above this plane, outwards towards the plane of OH and H. So this carboxyl group is behind the plane, this is towards you outside of the plane, and OH and H are on the plane that you are observing. Now if you are going to place a mirror, then this is the mirror image of this compound. The mirror images of each other, these two isomers are called enantiomers. The mirror image of one compound, these two are called enantiomers, which are non-superimposable. If you are going to try to place this compound on this compound, hydrogen is going to clash with the carboxyl group. So it is not superimposable on one another. This is another representation of the same molecule. The positive sign indicates that this compound or this enantiomer is a dextrorotatory compound. Means it is going to rotate the plane of the polarized light towards right. And this enantiomer is going to rotate the plane of the polarized light towards left. The negative sign is indicating. Now students, if we are going to take equimolar mixture of both positive and negative, then it is going to be a racemic, means equal, equimolar mixture. it is not going to be optically active because both of them are going to cancel out each other's effect due to the similar ratio. Now you can see the difference in the melting point of the dextroisomer, which is 26 degrees Celsius, and that of levoisomer is 26 degrees Celsius. Now the difference is only in the spatial arrangement, means three-dimensional arrangement. The melting point of the equimolar mixture is 18 degrees Celsius. Thus, three forms of lactic acid are known. Two of them are optically active and one is optically inactive, means which cannot rotate the plane of the polarized light towards any dimension. Students, let us study optical isomerism in tartaric acid, which is 2,3-dihydroxybutane dioic acid. Just like lactic acid, the positive isomer is going to be dextrorotatory. It is going to rotate the plane of polarized light towards right. Levorotatory is going to rotate the plane of polarized light towards left. And the equimolar mixture or the racemic mixture is optically inactive. Students, here are the four optical isomers of tartaric acid. Now look at the first one. It is the positive isomer, which is going to rotate the plane of polarized light towards right. The mirror image of this positive isomer is the negative or the levorotatory isomers. Since they are mirror images of each other, therefore they both are called enantiomers of each other. And both of them are optically active because they are rotating the plane of the polarized light towards right or left. Now here is another isomer. Isomer means same molecular formula but different arrangement of atoms. Now you can see that this is the same molecular formula that can be written in another form. But students, this is not a chiral compound anymore now because you are having a plane of symmetry. Means if you are going to divide this molecule through this plane, you will obtain equal halves, which is not possible in the negative isomer as well as in the positive isomer. So whenever there is lack of chirality in a compound, it is going to be optically inactive. This is the meso acid. Equimolar mixture means the positive and negative isomer or the racemic mixture is also optically inactive. So these are the four isomers of tartaric acid. Students, the last topic of today's lecture is benzene and dye-substituted benzene. Michael Faraday discovered benzene in 1825 during the destructive distillation of vegetable oil, and Hofmann isolated it from coal tar. As a functional group, benzene and substituted benzene are called arenes. It was discovered by Michael Faraday, isolated by Hofmann. The molecular formula is C6H6, molecular weight is 78, and the special features of benzene is that it possesses resonance and it gives electrophilic substitution reactions. Now students, let us start with the nomenclature of mono-substituted benzene, means a benzene ring having only one substituent. The following procedures are adopted for naming mono-substituted benzene. The first rule is the parent name is benzene, and you know students that parent name is always written at the end. The substituent is indicated by prefix. For example, it might be a methyl, ethyl, chloro or nitro group, etc. Now look at the first example. This is chlorobenzene. The substituent is chloro and the parent is benzene. Similarly, this is nitrobenzene having a nitro substituent. Another example is bromo because it contains a bromine atom as a substituent. The name is bromobenzene. Now students, the substituent and the benzene ring taken together may form a new parent name. But over here, the largest parent name is preferred. For example, C6H5 and CH3 may be named as methylbenzene or phenylbenzene. According to the largest rule, methylbenzene is preferred. Now students, this is an alkyl group and benzene is an aryl group. Mostly, we have seen in nomenclature that we take alkyl groups as parent. So the name can be phenyl methane. But when such a case exists, then according to the rule, the largest rule is applied. Means the member which is going to have a larger ring or molar mass is going to be the parent name. Therefore, methyl being a smaller group is not taken as the parent. Instead, benzene is taken as the parent substituent. So the name is methyl benzene. Students, in organic chemistry, many aromatic compounds, means benzene containing compounds, have been known by their common or trivial names, which are still used. IUPAC system retains these names. A few are given below, and you will see that even in IUPAC naming, we are going to use these names. Whenever a benzene is attached with a methyl group, the name of this whole compound is toluene. Similarly, if NH2 is present along with benzene, it is called aniline. If a vinyl group is present, CH, double bond CH2, this is a vinyl group along with benzene is called styrene. A carboxyl group with benzene is called benzoic acid. And you are familiar with this compound. A OH group along with benzene is called phenol. OCH3 and benzene, you can see it is an ether linkage, R-O-R. When OCH3 is present, it is called anisole. If nitro group is present along with benzene, it is called nitrobenzene. And if bromine is present, it is called bromobenzene. Similarly, if isopropyl group, what is isopropyl? When a propyl is attached to the chain with the second carbon atom, it is called isopropyl. When it is attached to benzene, the common name is cumene. Now students, let us see how IUPAC rules name monosubstituted benzene. Monosubstituted derivatives of benzene are named by prefixing the name of the substituent to the word of benzene. For example, chlorobenzene, nitrobenzene and bromobenzene.